Okay, so now we're going to go ahead and start talking about the sun's solar insolation, at which latitude it's going to have its subsolar point, and how that's going to influence our seasons. So why do we have distinct seasons? Well, seasonality results from changes in the sun's altitude, how high the sun is in the sky, and you'll see some examples of the midnight sun in the northern and southern hemisphere. It also results in the changing of the subsolar point. So we identified that there's a range at which the subsolar point can be 90 degrees between 23.5 degrees north and 23.5 degrees south. And then also that's going to influence our day length. And so these changes are the results of the Earth's revolution, rotation, the axial tilt of 23.5 degrees, the sphericity, and the axial parallelism. So let's go ahead and look at two of the extreme scenarios. These are basically the 23.5 degrees north, which is going to represent June 21st, and 23.5 degrees south, which represents December 21st of our subsolar point. Okay, so let's go ahead and talk about December 21st solstice. Now, for us in the Northern Hemisphere, we identify that December 21st is the shortest day of the year. Now, you should, as soon as you think of the shortest day of the year in the Northern Hemisphere, you should immediately think that, well, in the Southern Hemisphere, we know that the subsolar point has reached its height of its maximum ability at 23.5 degrees south, and so therefore, Southern Hemisphere is experiencing summer, and they are experiencing the longest day of year as a result of the subsolar point's location on the Tropic of Capricorn. Okay, also it's important that, you know, when I was back in elementary school, I often learned of the summer solstice and winter solstice, but that terminology, you know, only refers to, you know, the Northern or Southern Hemisphere. So we switched to using December and June so that it reflects what's taking place in the Northern and Southern Hemisphere. So just remember that it's reversed. So on December 21st, it's the shortest day in the Northern Hemisphere and it's the longest day in the Southern Hemisphere, winter versus summer. Now let's go ahead and jump to the image on the right. Now the subsolar point is at its highest extent at 23.5 degrees north, and this is going to be at the Tropic of Cancer. Now, for us in the Northern Hemisphere, this is the longest day of the year. For those in the Southern Hemisphere, it's now the shortest day of the year because they are so far removed from that subsolar point. Now, that's going to be very important as we move forward. Okay, so let's now incorporate two other important dates on the calendar. So we talked about June 21st and we talked about December 21st. Now let's go ahead and incorporate the Earth's orbit and the axial tilt and tie that into our discussion here. So on June 21st, we know that the subsolar point is at 23.5 degrees north, and it's summer in the Northern Hemisphere and it's winter in the Southern. Okay, so now let's go ahead and look at what June 21st looks like on our diagram here. So we know that the tilt of the Earth doesn't change. It's a fixed 23.5 degrees. But notice that on June 21st, that tilt is towards the sun. So now we're tying in the axial tilt. It's tilted towards the sun, where our subsolar point is at 23.5 degrees north. Now let's go ahead and flop over to December 21st, which is going to be our December solstice. And notice the axial tilt. The Earth is tilted away from the sun. So that supports that the subsolar point is at 23.5 degrees south in the Southern Hemisphere, and that the Northern Hemisphere is not receiving the insolation, the same amount of insolation as the Southern Hemisphere. Okay, so now let's go ahead and add two more calendar dates and discuss on why this is so important. So March 21st is often described as spring in the Northern Hemisphere and autumn in the Southern Hemisphere. Now, we also use the terminology of equinox to describe this period of time. We use it for March 21st and September 21st. Now, equinox meaning equal daylight, equal night time. So 12 hours day, 12 hours night. And this can be identified on March 21st and September 21st. Okay, so let's go ahead and look at the December solstice with a little bit more detail. And I really like these diagrams because the sun angle and the subsolar point are actually drawn on here. From a mathematical standpoint, we get a great depiction of the angle of the sun. Okay, so December solstice, where's the subsolar point? Everyone should be chiming in and saying 23.5 degrees south. And we actually see that. We see that 90 degrees subsolar point drawn. So meaning that the sun's solar insolation is striking the Earth at a 90-degree angle. Now we see that that's the only spot on the Earth's surface that has the intensity of the 90 degrees direct solar insolation. We also, on the left-hand side of the diagram, we see that the hours of day. So notice that in the southern hemisphere, around the Antarctic Circle, researchers that are down in Antarctica are receiving almost 24 hours of complete sunlight due to the subsolar point and the intensity of that location. So we also can compare folks that are living above 66.5 degrees in the Arctic Circle, and they're receiving 0 hours of daylight at this period of time. So it helps us identify the distribution of the day length. Now, another great a diagram that helps solidify, the range of our subsolar point and at which dates on the calendar year the subsolar point is located. I typically go ahead and look at the extremes. So I look at the June 21st, Tropic of Cancer, check, understand that. December 21st, Tropic of Capricorn at 23.5 degrees south. Yep, we know about that. Okay, so now let's go ahead and tie in March 21st and September 21st. Now we identified those dates as being the equinox. Okay, so where should the subsolar point be? Well, it kind of makes sense. It should be at the equator. So equinox, equator, equal day, equal night. Now we have the subsolar point appears at this location twice a year, March 21st and September 21st. And we see that solar insolation is at 90 degrees at 0 degrees of latitude at the equator. Now let's go ahead and look what this December solstice looks like in the southern hemisphere. Now this is a time-lapsed image showing the location of the sun in the sky over the December period. And we have almost the 24 hours of daylight. The sun really doesn't set. And this should be similar to what we'll see in the northern hemisphere during the June solstice. Okay, so another great diagram depicting the hours in the day versus the sun's angles and the subsolar point. So now we're talking about the June solstice. Again, June solstice, the highest extent of the subsolar point is going to be at 23.5 degrees north at the Tropic of Cancer. All other angles are going to be less than 90. But we know that during this period of time in the northern hemisphere, it's summer. So anyone that lives above 66.5 degrees north is going to be experiencing 24 hours of daylight. We know that for us at our latitude, at the mid-latitudes, we have, the sun starts to set around 9 o'clock on those summer evenings. And so we experience the longest day of the year at this period of time. Well, different story for those folks in the southern hemisphere. Above 66.5 degrees of the Antarctic Circle, they have 0 degrees of sunlight at that period of time. Having lived up in Alaska and worked the summers during the June solstice, I will say it's a pretty amazing thing to see the sun. This is a time-lapse picture of the sun trying to set. This is also referred to as the midnight sun. It really doesn't go down at its lowest point in time. You can see it kind of in the middle of the screen. It's its lowest angle in the daylight, and it never sets. So imagine trying to sleep during this period of time, but it actually lends to some really long work days out in the field. Okay, so let's go ahead and talk about the equinox now. So the equinox, we know that this happens twice a year, where the subsolar point is at the equator. Good. Okay, so we know that this period of time, we can see this, looking at our circle of illumination, night and day. We see that all across the globe, we are experiencing 12-hour days. at every single line of latitude, going from 90 degrees north to 90 degrees south. Okay, and this happens twice a year. So what I want to show you here, this is called an analemma, and this is a time-lapse photo that was taken of the sun's location at the same location once a day. And the sun appears at its highest point in the analemma during the summer and its lowest during the winter. And you can see that this is basically depicting the range of the subsolar point. You know, we see where the analemma crosses over itself twice. This is going to be during the equinox. And at here, when it's at its highest extent, the sun, this is going to be during the summer period. And this is going to be when the sun's lowest is going to be during winter. And a pretty amazing photo. This was actually taken in 1998 in August through 1999 August, so a whole year in Ukraine. And so it really gives you an indication of these different periods of time within the calendar year and where the subsolar point is at, where the sun is at its highest and lowest point. Now this should look very similar. This is a reference analemma that is often found on a globe that helps geographers determine the daylight and the subsolar point on an actual globe. So a very helpful tool for geographers to recreate, you know, the range of the subsolar point and have it be a useful tool for calculations on a globe. Okay, so we are going to be calculating the sun's angles today in this week's class discussion. So basically, in order for us to be able to calculate the sun's angles, all we need to know is the latitude of where you're at, which is often described as the observer, and the solar declination, so the angle of the sun. So example, what is the sun angle in Reno at noon on August 27th? So what we need to know is, where are we? Are we in the northern hemisphere? Are we in the southern hemisphere? And what's our latitude at? And then where is the subsolar point? So then other questions to ask yourself are we in the northern or southern hemisphere? So summer or winter hemisphere. So two equations that we are going to be using for this calculation is going to be a same hemisphere equation versus a different hemisphere. So same hemisphere meaning that the observer's latitude and the declination is going to be in the same hemisphere, meaning they're in the both in the northern hemisphere, both in the southern hemisphere. If the observer is in the northern hemisphere and the solar declination is in the southern hemisphere, then we're going to use the different hemispheres equation. And the elements that come into this equation is D, represents the declination, so the latitude of the subsolar point. L is the latitude of the observer, and S is going to be what we're calculating. So some questions to ask yourself: summer or winter hemisphere? So you are in Boise, Idaho, and the sun is at the Tropic of Cancer. Okay, so what is the latitude of the Tropic of Cancer? Tropic of Cancer is at 23.5 degrees north, and you are in Boise, Idaho. Now, we don't know the latitude of Boise, Idaho right off the top of our head, but we do know that it is in the northern hemisphere. So we would be using the same hemisphere equation for this particular problem. A second one is you are in Sydney, Australia, and the sun is at 12 degrees north. So basically, we would be using the different hemisphere equation because we know that Sydney, Australia is in the southern hemisphere and the sun is at 12 degrees north. Okay, here's another scenario. You're in Lima, Peru, and the sun is at the equator. Okay, so Lima, Peru, that's going to be kind of tricky. This is a tricky one. So the equator is kind of this neutral zone. So you're able to use either one of the equations for the northern hemisphere or southern hemisphere to complete the problem. So we can go ahead and use the example of Reno, Nevada. So Reno is at 39.5 degrees north and the subsolar point is at 10 degrees north. So we're going to be using the same hemisphere equation. So the equation looks like this. We have some absolute values, which means if the calculations is going to be negative, that it's going to show up as a positive number on here. So we're going to take 90 degrees minus the absolute value of the observer at 39.5 minus the subsolar point. And the answer gives us a 63.5 degree sun angle at this period of time.